A faint glow fills the cosmos, completely invisible to our eyes. This is the cosmic infrared background, a pervasive light that represents one of astronomy's greatest unsolved puzzles. By the end of this journey, you will uncover 25 profound mysteries hidden within this universal glow that are reshaping our entire story of the cosmos. We will investigate the origins of this enigmatic radiation and ask what forgotten galaxies or exotic physics could be casting this cosmic shadow. Are we truly prepared for the secrets the universe has been keeping in plain sight, yet just out of view? This faint, all-encompassing glow is our first great mystery. What is the true source of the light that fills the entire sky? This is not the sharp, pinpoint light of stars we recognize, nor the collected glow of familiar galaxies. Instead, it is a diffuse cosmic backdrop, a soft whisper of infrared radiation that comes from everywhere at once. Its very smoothness is the clue. A sky littered with known objects would look patchy and uneven, but this signal is a uniform veil, suggesting its origins lie in a population of sources so incredibly numerous and ancient that they blend together into a single universal light. The leading suspicion points to the very first structures to ever switch on in the cosmos. Picture the universe in its infancy, after the fading glow of the Big Bang, when it was a dark, vast sea of simple gas. Then somewhere the first stars ignited. These were not like the stars of today. They were likely behemoths, hundreds of times more massive than our sun, burning ferociously and dying young in spectacular explosions. Their brilliant light, stretched over billions of years of cosmic expansion, has now reached us as this faint infrared afterglow. Our most powerful telescopes strain to see them individually as they are too far, too faint, and shrouded in the primordial gas of the early universe. So we are left with their collective ghost, a background hum of creation's first dawn. What did those first stellar giants look like, and what secrets did they take with them when they vanished? The answer is written in this diffuse light, a message we are only just learning how to read. But this cosmic whisper holds another, even more perplexing secret. While the overall glow is remarkably smooth, our most sensitive instruments detect faint, lumpy textures within it. These are not random noise, they are real fluctuations, tiny blobs and patches of infrared light that stubbornly refuse to line up with any galaxy or star we can identify. Imagine looking at a vast, foggy landscape and seeing indistinct shapes moving just beyond the veil. You know they are there, you can measure their presence, but you cannot make out what they are. These infrared blobs represent a hidden population, a cosmic multitude that has entirely escaped our notice. Our deepest galaxy surveys have catalogued countless stars and systems, yet they have somehow missed these specific sources entirely. This forces a profound question. What are these ghostly objects and why have they remained invisible? One compelling idea is that they are incredibly faint, primordial galaxies from the universe's first billion years. These infant systems, filled with the first generations of stars, would be so distant and shrouded in cosmic dust that their light is reduced to these faint smudges in the background. They are the building blocks of the giant galaxies we see today, but we are catching them at their moment of birth, too dim and diffuse for our telescopes to resolve individually. Another, more exotic possibility is that they represent something entirely unforeseen. Perhaps galaxies so choked with dust that their visible light is completely absorbed and re-radiated as the infrared we now detect. Each of these unexplained blobs is a clue, a piece of a puzzle that could rewrite our entire story of how galaxies form and evolve. If our cosmic censuses are missing entire legions of objects, what else have we gotten wrong about the universe's history? The hunt for these ghostly objects leads us directly to two of the deepest enigmas written into the infrared glow. We are searching for the very first galaxies, the foundational structures of the cosmic web. According to our best models, the universe's infancy should be ablaze with their formation. and their brilliant light, stretched by time, should shine brightly in the infrared background we observe. Yet they remain almost entirely elusive. Why can we not see them? One possibility is that they are simply too faint, their stellar fires too weak to pierce the vast cosmic distances to our telescopes. But another, more intriguing idea is that they are shrouded, hidden behind immense curtains of cosmic dust. In this scenario, a primordial galaxy would form its first stars, whose intense visible and ultraviolet light is immediately absorbed by the thick clouds of dust and gas within the galaxy itself. This dust heats up and re-radiates the energy, but now as a much longer, invisible infrared wavelength. It is like trying to see a lighthouse in a dense fog. You only perceive the diffuse glow around it, not the beacon itself. So the very act of creation in the early universe might be self-concealing, hiding its most brilliant moments from our view. This directly connects to an even more profound quest, the search for the very first stars. Theorists call them population 3 stars. These were not just ancient stars, they were the first factories of matter in the cosmos, forged from only the primordial elements of hydrogen and helium. Nothing else existed. This pure composition meant they burned at ferocious temperatures, grew to colossal sizes, and lived short, violent lives ending in titanic explosions. Their death cries were essential, for it was in these explosions that the first heavy elements like carbon and oxygen, the very building blocks of planets and life, were forged and scattered across space. The intense ultraviolet light from these stellar giants, after traveling for billions of years, should be stretched or redshifted directly into the infrared part of the spectrum. Its signature should be imprinted on the cosmic infrared background like a fingerprint on a window pane, but after years of searching, that definitive fingerprint has yet to be found. Their predicted signal is missing, so we are left with a haunting question. Did population 3 stars ever truly exist in the numbers we believe? Or does their absence in the data mean we have misunderstood the very conditions of the universe's first dawn? The answers are hidden within that faint, all-pervasive glow, waiting for the right moment to reveal themselves. Beyond the hunt for lost stars and galaxies, the infrared background whispers of even more exotic possibilities. Some scientists are probing the very nature of the cosmos itself, suggesting this faint light could be a signal from the invisible realm of dark matter. We cannot see dark matter directly as it does not emit, absorb, or reflect light, yet its gravitational pull is the only thing holding galaxies together. So how could it possibly create light? One compelling theory involves dark matter particles interacting with each other. If 2 of these particles were to collide and annihilate, the process could potentially release energy in the form of gamma rays or, crucially, lower energy infrared photons. It is a faint, universal process that could be happening all across space, contributing a subtle, steady drizzle of light to the cosmic infrared background. Finding this signature would be like finally hearing the voice of a ghost that we have only ever seen by its shadow. This leads to a related and equally profound mystery. What if other exotic particles, relics from the universe's fiery birth, are also decaying and adding to this glow? In the incredibly dense and hot conditions just after the Big Bang, physicists believe a whole zoo of strange particles may have briefly existed before most of them vanished. Some of these could have been just stable enough to survive into the present day, only now to be slowly, quietly decaying away. Each decay would release a tiny bit of energy, and if these particles were numerous enough, their collective death over billions of years could produce a detectable infrared signal. We are essentially searching for the fossilized remains of the universe's first moments, not in rock but in light. The smooth, pervasive nature of the infrared background makes it the perfect hiding place for such a universal process. Perhaps the most startling proposal involves not particles, but tiny black holes born in the chaos of the Big Bang. These are not the stellar black holes formed from collapsing stars, but primordial black holes, which could have been forged from the intense density fluctuations in the universe's first second. They could range in size from a speck of dust to a small asteroid, and they might be everywhere, drifting unseen through the cosmos. So how would something that famously absorbs light end up producing it? The answer lies in their environment. If a primordial black hole were to pass through a cloud of interstellar gas and dust, its immense gravity would violently compress and heat the material around it. This heated dust would then glow brightly in the infrared, creating a brief, localized point of light before fading away as the black hole moves on. A vast population of these objects, each occasionally flaring up as it interacts with matter, could collectively paint a portion of the infrared background we observe. The thought that this cosmic static could be the accumulated flicker of countless ancient black holes forces us to reconsider the very fabric of our reality. This pervasive infrared glow reveals a hidden ingredient that should not be there: cosmic dust on a colossal scale. We are not talking about the simple dust you find in a corner of your house. This is interstellar dust, microscopic grains of carbon, silicon, and other heavy elements forged in the nuclear furnaces of stars and scattered by their violent deaths. The mystery is not just that this dust exists in the early universe, but that it appears in staggering amounts far earlier than anyone thought possible. When we look at the infrared background, a significant portion of that light is the warm, re-radiated glow from countless trillions of these tiny particles, heated by the starlight of the first galaxies. The enigma is one of time, or rather, a lack of it. According to our standard cosmic timeline, the universe was too young for this to happen. The very first stars had to form, live their short, brilliant lives, and then explode as supernova to produce the first heavy elements and spew them out into space. Those elements then had to cool, condense, and form solid dust grains. This entire cycle takes time, generations of stars living and dying to build up the cosmic inventory of dust. Yet the infrared background tells us that when the universe was only a few 100 million years old, a mere toddler in cosmic terms, vast clouds of dust were already blanketing infant galaxies. It is as if you walked into a newborn nursery and found the walls already covered in the soot from 1,000 industrial revolutions. How did the universe manage to get so dirty so incredibly fast? One possibility pushes stellar evolution to its absolute limit. Perhaps the very first stars, those monstrous population 3 giants, were even more efficient dust factories than we dreamed. Their titanic explosions could have been so powerful and so rich in heavy elements that they produced immense quantities of dust in a single, catastrophic generation. Another, more radical idea is that we are missing a completely different pathway for dust creation. Could supernova have helped? What if the violent winds from growing supermassive black holes at the hearts of these early galaxies, known as quasars, churned out dust as a byproduct of their ferocious energy? Or perhaps there is a mechanism we have not yet considered, a way for dust to condense directly in the cooling ejecta of certain types of stellar explosions without needing multiple generations of stars. Each of these tiny dust grains, invisible on its own, collectively forms a curtain that obscures our view of the cosmic dawn, and their premature presence in the universe is a clue that the story of how everything began is far from complete. This cosmic dust enigma is deeply intertwined with another, even broader mystery that has haunted astronomers for decades. We have somehow misplaced half of the ordinary matter in the entire universe. This is not the invisible dark matter, but the normal stuff, the atoms that make up stars, planets, and us. Our most precise calculations of the universe's composition tell us exactly how much of this baryonic matter should exist, yet when we add up everything we can see, from the brightest galaxies to the faintest gas clouds, nearly half of it is simply gone. This is the infamous missing baryon problem. Where could an entire universe worth of atoms be hiding? the leading suspect is a vast, diffuse web of incredibly hot gas, known as the warm-hot intergalactic medium. Picture the cosmic web not just as a structure of galaxies, but as a labyrinth of invisible filaments with superheated gas trapped within them. This gas is so tenuous and so scorching hot that it does not emit the kind of light our telescopes are designed to easily catch. It is a ghost in plain sight, so how do we find it? This is where the cosmic infrared background offers a crucial clue. As that superheated gas floats in the space between galaxies, it is constantly being bathed in the light from all the stars and galaxies throughout cosmic history. This ambient radiation, particularly the energetic ultraviolet light from quasars and young stars, can interact with the gas, causing it to glow with an extremely faint specific signature. Some of that emission, stretched by the expansion of the universe, could very well be contributing to the very infrared background glow we are trying to decipher. The infrared sky might be acting like a gigantic projection screen, displaying the faint, accumulated glow of this missing matter. Finding this specific signal within the background's uniform light would be the ultimate cosmic treasure hunt, allowing us to finally map the invisible skeleton of the cosmos. It would confirm that the universe's ordinary matter is not missing at all. It has just been hiding in the hardest place to look, the vast, empty spaces between everything. The universe's infrared glow holds another secret in its subtle grain. It is not perfectly smooth as one might expect from a truly uniform veil. Instead, it possesses a faint texture, a set of patterns and directional preferences that scientists call anisotropies. These are not random imperfections, they are real irregularities in the background light, and they point in directions that do not match the map of any galaxies we can see. It is as if you were listening to a constant, soft hum and began to detect a faint, rhythmic beat underneath, a pattern that does not come from any visible source. What could possibly cause the entire sky to have a preferred direction, a subtle lumpiness that defies our expectations? One of the most profound possibilities is that we are seeing the ghostly imprint of the universe's largest structures, woven into the fabric of space during the first fleeting moments after the Big Bang. In that initial violent expansion, quantum fluctuations were stretched to cosmic proportions, creating seeds that would eventually grow into the vast cosmic web of filaments and voids we see today. The infrared background's anisotropy could be a fossilized map of those primordial seeds, a pattern set in place before the first star ever flickered into existence. This would make the infrared sky a direct window into the universe's infancy, a snapshot of its potential before structure ever formed. Another, more exotic explanation involves cosmic strings. These are not strings in the everyday sense, but theoretical, unimaginably dense flaws in the fabric of space-time, thinner than a single atom but stretching across the entire cosmos. Think of them as cracks that formed as the universe cooled and expanded, much like cracks forming in ice. Their immense gravitational influence would warp the space around them, subtly tugging on matter and light. As the universe evolved, the ghostly presence of these cosmic strings could have guided the formation of the first structures, leaving a distinct, directional signature etched into the infrared background we observe today. Finding their fingerprint would be like discovering the original architectural plans for the cosmos. These anisotropies are more than just statistical curiosities, they are a potential Rosetta Stone. By deciphering their patterns, we could learn what triggered the formation of everything we see. Were the initial quantum fluctuations truly random, or was something else at work? The directionality of the infrared glow might be our first clue to answering that ultimate question, a whisper from the beginning of time itself, waiting in the static of the sky. The subtle patterns in the infrared sky might be tracing an event that transformed the entire cosmos. This is the cosmic reionization echo, a fossilized record of the universe's great awakening. After the first stars and galaxies ignited, their intense ultraviolet radiation began to tear apart the primordial fog of neutral hydrogen that filled all of space. It was a cosmic dawn in the truest sense, a billion-year-long sunrise that burned away the mist and made the universe transparent to light for the first time. The energy from that colossal event, the cumulative flash of countless first lights, did not simply vanish. After traveling for billions of years, stretched by the expansion of space, it should now reside as a specific, subtle signature woven into the cosmic infrared background. Detecting this echo would be like finding the faded photograph of the universe's most important transition, a direct glimpse into the era when the cosmic dark ages finally ended. This profound change connects directly to some of the most bizarre and beautiful objects we have ever found, the Lyman alpha blobs. These are not galaxies in any ordinary sense. They are immense clouds of hydrogen gas, some of the largest single structures in the entire universe, each one spanning hundreds of thousands of light years. They glow with a specific, powerful wavelength of light, and they are ferociously bright in the infrared. Their sheer scale and brilliance suggest something extraordinary is happening within them, perhaps a frenzy of star birth on a scale we can barely comprehend, or the intense radiation from a hidden supermassive black hole at their core. What is their role in the cosmic story? These colossal blobs could be the powerhouses of the reionization era, the very engines that helped clear the cosmic fog. Their immense infrared output, a product of their hidden turmoil, is almost certainly a significant contributor to the background glow we see. Yet we do not fully understand what makes them shine so brightly or why they exist at all. Are they the cradles of the universe's first giant galaxies, caught in a violent and brief phase of construction? Or are they something else entirely, a type of cosmic structure we have not yet classified? Each of these glowing behemoths is a piece of the reionization puzzle, and their light, now blended into the infrared background, is a constant reminder that the universe's most dramatic moments are still echoing all around us. This faint infrared static might be the collective whisper of countless lost galaxies. Our most sophisticated computer simulations of the universe predict a cosmos teeming with dwarf galaxies, small, faint collections of stars that should vastly outnumber the giant spirals and ellipticals we see. They are the predicted building blocks of larger galaxies, the cosmic bricks from which everything is assembled. Yet when we point our telescopes at the sky, we find a puzzling shortage. Where are they all? The answer may be that we are already seeing them, not as pinpoints of light, but as a collective glow in the cosmic infrared background. These missing dwarf galaxies could be so intrinsically faint or so shrouded in dust that our telescopes cannot pick them out individually from the darkness. Instead, their combined, unresolved light simply blends together into the uniform veil we detect. It is like trying to see individual fireflies from a mile away. You would only perceive a faint collective haze. This connects directly to a fundamental cosmic census known as the faint end of the luminosity function. This is simply a tally of how many bright galaxies versus how many faint galaxies exist. Our observations suggest there is a steep drop-off in the number of very dim galaxies, but the infrared background strongly implies the opposite, that the universe is absolutely packed with them. The discrepancy is staggering. It means our standard picture of galactic populations, the very hierarchy of the cosmos, could be fundamentally incomplete. We may be missing the vast, silent majority of galaxies, the faint cosmic proletariat whose combined light forms the backdrop against which the brilliant aristocrats, the galaxies we can see, are displayed. Adding to this hidden multitude is a more ghostly component, the intracluster light. In the immense gravitational pools of galaxy clusters, hundreds or even thousands of galaxies are bound together. As these galaxies swing past one another over billions of years, their gravitational tides violently pull at each other, ripping away countless stars. These orphaned stars do not belong to any galaxy anymore. they are flung out into the dark spaces between, forming a faint, diffuse fog that permeates the entire cluster. This is the intracluster light. While each individual star is a dim candle, their collective numbers are so immense that this phantom glow can be a significant source of radiation. And just like the faint dwarf galaxies, the specific infrared light from these vast clouds of wandering stars is thought to blend seamlessly into the cosmic infrared background. The universe, it seems, is filled with ghosts, the phantom glow of lost galaxies and the wandering souls of stars cast adrift, their combined voices creating a hum that fills the silence. This faint, universal glow faces a deceptive rival much closer to home. An eerie light sometimes appears in the night sky just after sunset or before sunrise, a soft, pyramid-shaped radiance stretching up from the horizon. This is the zodiacal light, and it is not a distant cosmic mystery but a local phenomenon. It is sunlight scattered by countless trillions of dust grains that orbit our own sun, a vast, flat cloud of debris left over from the formation of the planets. For astronomers trying to measure the true cosmic infrared background, this nearby glow is a formidable contaminant. It is like trying to hear a whisper from across a crowded, noisy room where the loudest voice is your own. The challenge is that this solar system dust emits and scatters light in the exact same infrared wavelengths that we are trying to use to probe the early universe. Before we can even begin to study the cosmos's first light, we must first perfectly subtract the glow from our own celestial backyard. This process of foreground subtraction is one of the most delicate and critical tasks in modern cosmology. A tiny error, an overestimate or underestimate of this local dust, can create a false signal in the cosmic background data, making it appear as if we have detected a profound cosmological phenomenon when we are actually just seeing the amplified echo of our own solar system. How do scientists perform this cosmic subtraction? They use the motion of the Earth itself as a tool. As our planet travels around the Sun, our viewpoint through this interplanetary dust cloud changes. By measuring the infrared sky from different points in Earth's orbit, astronomers can map the subtle variations in the zodiacal light and build a detailed model of its structure and intensity. Spacecraft positioned far from Earth provide another crucial vantage point, helping to triangulate the true foreground signal. It is a painstaking process of peeling away layers, like an art restorer carefully removing centuries of grime from a masterpiece to reveal the original painting beneath. The integrity of our entire understanding of the cosmic infrared background rests on this precise, unglamorous work. If we get it wrong, we are not just misreading a single signal, we are building our story of the universe's infancy on a foundation of local dust. There is a deep conflict brewing in the measurements of the universe's total light. When astronomers add up the light from every single galaxy we have ever observed, from the brilliant nearby spirals to the faintest smudges at the edge of our vision, they arrive at a number. This is the integrated light of the known cosmos. Separately, they can measure the extragalactic background light directly, the total glow that fills the space between galaxies, which includes our cosmic infrared background. In a perfect and complete understanding of the universe, these two numbers should match perfectly. The sum of all the parts should equal the whole, but they do not. There is a stubborn discrepancy, a gap between the light we can account for and the light that is actually there. This is the extragalactic background light dichotomy, and it is a glaring sign that our cosmic inventory is missing entire chapters. What incredible sources of illumination are we failing to see? The missing light almost certainly comes from populations of galaxies that remain hidden from our view. Our most powerful telescopes like Hubble and James Webb are incredible, but they have their limits. They can see the bright, mature galaxies, but they might be completely blind to an entire class of faint, diffuse, or extremely dusty systems. Imagine trying to census a city at night by only counting the bright streetlights. You would completely miss the dim glow from house windows, the faint lanterns in backyards, and the distant lights from isolated farms. Your total count of the city's light would be far less than the true collective glow that a satellite would see from space. This is precisely the situation we face with the universe. The discrepancy tells us that the cosmos is filled with these cosmic house lights, sources too dim or too spread out for our current telescopes to resolve. They could be ultra-diffuse galaxies, vast collections of stars with so little density that they blend into the darkness of space. They might be galaxies that are shrouded in such thick, pristine dust that their starlight is completely converted into the infrared background we detect, making them invisible in the surveys that hunt for their visible light. Or they could be the very first galaxies, so incredibly distant that their light has been stretched into a faint, infrared whisper that simply fades into the noise. This dichotomy is more than a simple accounting error. It is a fundamental challenge to our understanding of cosmic structure. It forces us to ask how much of the universe's history is written in light we have not yet learned to read. Deep within the hearts of galaxies, cosmic monsters are feeding. These are active galactic nuclei, or a GN, the universe's most powerful and persistent engines powered by supermassive black holes. As immense amounts of gas and dust spiral inward toward the black hole's event horizon, the material compresses and heats to millions of degrees, unleashing a torrent of radiation that can outshine every star in its host galaxy combined. Much of this furious energy, especially if the black hole is shrouded in a thick, dusty donut, is absorbed and re-radiated as intense infrared light. This immediately presents a critical mystery for the cosmic infrared background. How much of that universal glow is actually the accumulated, muffled roar of these hidden monsters? We know they are out there, but our census is likely deeply incomplete. Our telescopes easily spot the blazing quasars, the AGN, that are facing us directly with a clear line of sight. But for every one of those, there could be several more that are turned away from us, their brilliant central engines completely obscured by vast, swirling clouds of dust. We only see the warm infrared glow from the outer dust clouds themselves, heated by the hidden fury within. It is like trying to count campfires in a foggy forest. You might only see the diffuse halos around the ones pointed away from you, completely missing their true number and power. This hidden population of obscured AGN could be a massive, unaccounted-for contributor to the infrared background. Their combined, muffled light might be woven throughout the cosmic static, a significant part of the signal we have been attributing to first stars and galaxies. Unraveling their specific contribution is like trying to isolate a single instrument in a grand symphony, where every player is hidden behind a curtain. The implications are profound. If a large portion of the background comes from these hidden black holes, it would mean that the growth of supermassive black holes was an even more dominant and frenzied process in the early universe than we ever suspected. It would reshape our understanding of how galaxies and their central black holes co-evolved, suggesting that these dark engines played a far greater role in heating the cosmic dust and shaping the infrared sky than the stars themselves. The faint glow that fills the cosmos might not just be the gentle whisper of creation, but also the stifled roar of destruction echoing across time. This faint glow is the universe's grand ledger, a permanent record of every star that ever burned. The cosmic infrared background should encode the total energy output from all stellar furnaces across cosmic time, a sum of every sunrise in every galaxy since the beginning. It is the final tally of the universe's star formation history. Yet when we use this ledger to reconstruct that history, the numbers do not add up. The story told by the infrared background conflicts with the history we have pieced together from other, more direct observations. This is the cosmic star formation history enigma, a fundamental disagreement over the universe's most creative period. How can we be so wrong about the very timeline of creation itself? One method for writing this history involves looking at galaxies at different distances. Because light takes time to reach us, a galaxy 1 billion light-years away is a snapshot of the universe 1 billion years ago. By surveying vast numbers of galaxies at different cosmic epochs, we can estimate how quickly stars were being born at each point in time. This method paints a specific picture, a cosmic boom where star formation rates rose to a peak around 10 billion years ago and have been steadily declining ever since. But when we analyze the infrared background, which is the integrated light from all these eras combined, it suggests a different narrative. The total energy in the background seems to imply that there was more star formation, especially in the very early universe, than our galaxy surveys can account for. It is as if the financial records of a giant corporation show a massive, unaccounted-for income stream. Where did all this extra light come from? The most likely explanation is that our galactic census is missing a vast, hidden population of stars. Our surveys are biased toward the bright and the beautiful, the galaxies that are easy to see. We are likely missing legions of faint, dusty, or extremely distant galaxies whose collective light is significant but whose individual identities are lost in the glare of their brighter cousins. These unseen stellar factories would have been working overtime in the early universe, their contribution now baked into the infrared background but absent from our history books. Another possibility is that we are misjudging the efficiency of stars themselves. Perhaps the first stars were fundamentally different, converting more of their mass into light than the models predict, or burning in a way that produced a greater infrared signature. The universe's ledger is telling us a story we have not yet fully deciphered, one that suggests the cosmic dawn was even more brilliant and prolific than we ever dared to dream. Even our own galaxy casts a deceptive shadow across the cosmic signal. Wispy, filamentary clouds drift through the vast spaces between our stars, glowing with a faint, cold infrared light of their own. Astronomers call this phenomenon infrared cirrus, named for its resemblance to high, wispy clouds on Earth. This is not the light of creation from the edge of time, but the local emission from cold dust grains right here in the Milky Way, warmed by the faint ambient starlight of our galactic neighborhood. These delicate structures are incredibly pervasive, and their faint glow is superimposed directly on top of the far more distant cosmic infrared background. Telling them apart is a monumental challenge, like trying to listen for a specific voice in a chorus while other singers are humming a similar tune right next to your ear. Each of these cirrus clouds is a unique structure with its own density and temperature, meaning its infrared signature is not a uniform noise that can be easily subtracted. It is a complex, textured veil that must be painstakingly mapped and peeled away, layer by layer, to reveal the true extragalactic sky behind it. This galactic cirrus is just one part of a much larger problem, the overwhelming complexity of our own Milky Way's foreground. Our galaxy is a brilliant, dynamic ecosystem of light. Billions of stars, from the faintest red dwarfs to the most luminous supergiants, pour their combined radiance into space. Vast nebulae where new stars are born glow with intense and specific colors. The diffuse glow from countless unresolved stars and the scattered light from cosmic dust create a complex, bright backdrop across the entire sky. All of this light, this entire galactic symphony, exists between us and the faint cosmic signal we are desperate to measure. To find the whisper of the first galaxies, we must first silence the roar of our own. The process of foreground subtraction is not a simple matter of turning down a dial. It requires building exquisitely detailed models of the Milky Way's structure and emission across every wavelength. Scientists must account for the distribution of stars, the properties of dust, and the physics of how light scatters and is re-emitted. Any imperfection in this model, any tiny misunderstanding of our own galactic home, leaves behind a residual signal. This false glow can then be mistaken for a component of the cosmic infrared background, leading us to see profound mysteries in the data that are, in reality, just the ghost of our own incomplete knowledge. The greatest challenge in seeing the dawn of the universe may not be the vastness of space, but the brilliant, complicated city of stars we call home. The very color of this cosmic light hides a profound contradiction. It is not enough to simply measure the intensity of the infrared background. We must also understand its spectrum, the precise way its energy is distributed across different infrared wavelengths. This is its spectral energy distribution, a unique fingerprint that should tell us exactly what kinds of objects are creating the glow. Yet when we analyze this fingerprint, we find a riddle. The shape of this spectrum does not perfectly match the combined light of any known sources, not from the first stars, not from dusty galaxies, and not from active black holes, no matter how we try to mix them. It is as if we had a precise audio recording of a symphony, but when we tried to recreate it by summing the sounds of every known instrument, the result was always slightly off, a dissonant chord that reveals a missing instrument, or perhaps an entirely new one we have never heard before. This mismatch implies one of two startling possibilities. Either there are exotic physical processes at work in the early universe that we have not yet accounted for, or our fundamental models for how galaxies and stars emit light are fundamentally incomplete. Consider our models for star formation. They are built on observations of galaxies in our local cosmic neighborhood, galaxies that are mature and have had billions of years to evolve. We assume that the first galaxies in their infancy operated by the same basic rules. But what if they did not? What if the first stars formed in a more frenzied, chaotic way, producing a different blend of light? Or perhaps the dust in these primordial galaxies was not like the dust we know today. Maybe it was made of purer materials or had different sizes and shapes, causing it to absorb and re-radiate starlight in a subtly different pattern, warping the spectrum we now observe. The spectral energy distribution riddle forces us to question the very physics we take for granted. Are we seeing the signature of something entirely new, a process that faded away as the universe aged and no longer exists in the cosmos we see today? The answer is written in the invisible colors of the sky, a cosmic cipher waiting for its key. This ancient infrared light is not the only cosmic background painting our sky. It shares the void with its far more famous sibling, the cosmic microwave background. This is the oldest light in existence, the cooled and stretched afterglow of the Big Bang itself, a snapshot of the universe when it was a mere 380,000 years old. While one background shows us the universe's fiery birth, the other reveals its long, slow childhood, the era of its first structures. These two universal glows are deeply, physically intertwined in a way that creates both a powerful tool and a new layer of mystery. The key to their connection is gravity's invisible hand. As the pristine light from the cosmic microwave background travels for billions of years to reach us, it does not fly through empty space. It passes through the evolving cosmic web of dark matter and galaxies, a distribution that is traced by the more recent infrared background. When this ancient microwave light encounters a massive cluster of galaxies or a vast filament of dark matter, the immense gravity of that structure acts like a lens, subtly bending the light's path. This phenomenon, called gravitational lensing, creates tiny, specific distortions in the pattern of the cosmic microwave background, minute wrinkles that would not otherwise be there. By meticulously analyzing these distortions, scientists can essentially use the infant universe's light to map the distribution of all the matter that grew after it. It is like using a flashlight from the beginning of time to illuminate the shadows of everything that came later, and the cosmic infrared background provides the guidebook for this map, telling us where to look for these immense gravitational pools. But this elegant partnership introduces a profound complexity. The maps do not always align perfectly. The distribution of matter inferred from lensing the microwave background can sometimes suggest a slightly different cosmic architecture than the one traced by the infrared glow of galaxies. This subtle tension hints at a deeper puzzle about how matter, both dark and normal, is truly arranged across the largest scales of space. Could there be vast reservoirs of matter that are traced by one background but not the other? Are we seeing the ghostly influence of unknown forces that shaped the cosmos after the Big Bang? The conversation between these two backgrounds, one from the beginning and one from the dawn of structure, is an ongoing dialogue that is refining our understanding of the universe's entire history, revealing that the story written in light is still being decoded. This ancient infrared glow is not a single, static photograph of the past. It is more like a layered film reel, with each frame capturing a different era of cosmic history, all projected onto the same screen. The great puzzle is how to separate these layers to determine which parts of the glow come from the universe's fiery youth and which are from its more settled adulthood. The light we measure is a grand total, a sum of contributions from every epoch, but to understand the story it tells, we must break it down chapter by chapter. The challenge is immense. We cannot simply rewind the tape. The infrared background from the very first galaxies is incredibly faint and has been stretched to the longest wavelengths, while light from more recent, dusty galaxies arrives at shorter infrared wavelengths. In theory, by carefully dissecting the background's color and its faint fluctuations across different wavelengths, we can create a rough timeline of its buildup. Yet the answers we get are deeply puzzling. The data suggests that a significant portion of this cosmic light was generated very early on, when the universe was less than a quarter of its current age. This points to a frenzied, hidden period of intense activity, where vast numbers of primordial galaxies or voracious black holes were pumping out infrared radiation at a rate that seems almost impossibly high. How could the infant universe have been so prolific so quickly? But then the story seems to shift. As we look toward the contributions from more recent cosmic times, the picture becomes murkier. There is evidence that another substantial part of the background originates from the last several billion years, a period when the universe was already mature. This implies that infrared bright objects like galaxies shrouded in dust from frequent stellar birth and death have remained major players throughout cosmic history. The evolution is not a simple story of a bright dawn followed by a steady dimming. It appears to be a tale with multiple peaks of activity, a symphony with several crescendos. This time evolution puzzle forces us to ask what kinds of cosmic engines were dominant at each era. Were the first galaxies inherently dustier than we thought? Or did supermassive black holes play a greater role in heating the cosmic dust in the early universe than they do today? The changing intensity of the infrared background over billions of years is a direct record of the changing conditions within galaxies themselves. A brighter background in a certain era means more dust was being heated by more intense starlight or more active black holes. By reading this timeline, we are essentially reading the biography of the universe's hidden side, the story of how cosmic structures grew, not just in size, but in their ability to obscure their own brilliant light. Unlocking this chronological sequence is the key to understanding whether our universe had one dramatic opening act or a series of recurring, hidden revolutions. Every mystery we have explored is ultimately framed by a single, profound limitation, our own vision. The cosmic infrared background was first mapped in detail by pioneering observatories like the Spitzer and Herschel space telescopes. These incredible machines revealed the faint, all-pervasive glow, turning a theoretical concept into a tangible cosmic frontier. Yet for all their power, they reached a fundamental barrier. They could see the forest, but not the individual trees. Their view was like looking at a city from a great distance at night, seeing its collective glow but being unable to pick out individual streetlights or house windows. This technological ceiling is why so many of these 25 mysteries persist. We have the questions etched into the sky itself, but we have lacked the eyes to see the answers. The next great leap in our vision is already underway, with a new generation of telescopes designed to see what has been hidden. The James Webb Space Telescope, with its colossal golden mirror and exquisite sensitivity to infrared light, is our most powerful time machine. It is not merely an improvement, it is a transformation. Where Spitzer and Herschel saw a smooth, enigmatic glow, Webb is designed to resolve that glow into its constituent parts, to pick out the individual first galaxies and stellar nurseries whose combined light creates the background. It can peer through the veils of dust to see the furious birth of stars in primordial galaxies, and perhaps even detect the unique chemical signature of those very first pure population 3 stars. But the journey does not end with Webb. On the horizon waits the Nancy Grace Roman Space Telescope, an instrument with a field of view 100 times larger than Hubble's. While Webb looks deeply at tiny, precious patches of sky, Roman will conduct a vast panoramic census of the entire cosmos. It will find the rare, the faint, and the bizarre by the millions, mapping the distribution of galaxies and the subtle distortions of space-time with unprecedented precision. Together, these observatories will act as a cosmic detective duo, one using a magnifying glass to examine the clues in exquisite detail, the other using a wide-angle lens to see how all those clues connect across the vastness of space. They will test every theory, from the nature of dark matter annihilation to the origin of the universe's first dust. They will hunt for the missing dwarf galaxies and measure the true timeline of the infrared background's buildup. Yet history suggests a thrilling possibility. Every time we have built a new window to the universe, we have not only found answers to our old questions, we have stumbled upon phenomena so completely unexpected that they rewrote all the textbooks. The greatest mystery of the cosmic infrared background may not be one of the 25 we have named, but the one still waiting in the dark, ready to reveal itself when we finally learn how to see. This faint infrared whisper is a direct echo from the universe's greatest awakening. The cosmic dark ages did not end with a gentle sunrise, but with a violent, billion-year-long blizzard of ultraviolet radiation. As the very first stars and galaxies ignited, their fierce light began to tear apart the primordial hydrogen atoms that filled all of space, ripping electrons from their nuclei in a process called reionization. The collective energy from this colossal event, the flash from countless first lights, did not simply vanish. After journeying across the cosmos for more than 13 billion years, stretched and cooled by the expansion of space, that very same light is now theorized to form a fundamental part of the diffuse infrared glow we detect today. Finding its specific signature within the background is the ultimate goal, like isolating the first note of a symphony from the hum of the entire concert hall. Why is this so crucial? Because that note holds the entire story of the universe's transformation from a simple, dark sea of gas into the complex, structured cosmos we see today. The timing and the sources of reionization are among the biggest open questions in cosmology. Did brilliant, massive stars do most of the work, or were the central black holes in early galaxies, blazing as quasars, the primary engines that cleared the fog? The answer is encoded in the pattern of the infrared background. If the light comes mostly from stars, the background's fluctuations should be relatively fine and grainy, reflecting the countless small sources. If quasars dominated, the pattern might be more clumpy, tracing the rarer, more powerful beacons. But the signal is incredibly subtle, a faint ripple superimposed on a sea of other, more recent light. Detecting it requires not just powerful telescopes, but brilliant statistical methods to tease this ancient echo from the chorus of later galaxies and local interference. Success would give us a direct window into that formative epoch, allowing us to witness, for the first time, the moment the universe turned on the lights and became transparent, setting the stage for everything that was to come. This dust enigma forces us to re-examine the very nature of stellar death in the infant cosmos. The sheer volume of dust detected so early implies an almost unimaginable frenzy of destruction, a rate of supernova explosions that would have made the early universe a perpetual cosmic fireworks display. Could the first stars have died in such spectacularly efficient ways that they littered space with dust in a single, catastrophic generation? the leading hypothesis suggests these primordial supernovae were fundamentally different from the ones we see today. A star hundreds of times more massive than our Sun would not just explode, it might completely tear itself apart in a pair instability supernova, an event so violent that no black hole remains. In these universe-shattering blasts, the internal temperatures and pressures would be perfect for forging immense quantities of heavy elements that rapidly condense into solid dust grains as the expanding debris cloud cools. One such stellar cataclysm could potentially seed entire galactic neighborhoods with enough dust to explain the infrared signal we see. But is this enough? Even with these extreme events, the timeline remains incredibly tight. This pressure has led astronomers to consider other, less dramatic but more numerous dust factories. What about GB stars? These are aging, swollen stars in a late stage of life, and in our modern universe, they are known to be steady and prolific producers of dust, blowing it out into space in gentle stellar winds. The problem is time. GB stars take billions of years to evolve to that stage, a luxury the early universe did not have. Unless, that is, the very first stars included a population that raced through their life cycles at breakneck speed, reaching the GB phase and pumping out dust in just a few 100 million years. It is a cosmic race against the clock where the slow, steady dust makers must somehow become sprinters. Perhaps the answer is not just in the stars themselves, but in the environments they created. Once even a small amount of stardust is released into the void, it could have acted as a seed. In the dense, cold molecular clouds where new stars were beginning to form, these initial grains might have grown rapidly, accreting more atoms from the surrounding gas, like a snowball rolling through a blizzard. This process of grain growth in situ could have amplified a small initial output of dust into the vast, obscuring curtains we detect. The universe, it seems, might not have needed an army of supernova, but just a few pioneers to provide the blueprint, with the cold, dark clouds of the cosmic dawn doing the rest of the work. The infrared background is the integrated signal of all these possibilities, a fossilized record of the universe's first attempts to turn brilliant light into solid, tangible matter. The absence of those countless dwarf galaxies points to a deeper, invisible architecture. Our most sophisticated simulations of cosmic evolution paint a universe teeming with dark matter halos. These are not physical objects, but vast, spherical clouds of the invisible stuff that forms the gravitational skeleton of the cosmos. The models are very clear. For every giant halo that hosts a galaxy like our Milky Way, there should be thousands of smaller halos swarming around it like moons around a planet. Each of these smaller halos possesses enough gravity to pull in ordinary gas, and according to our standard rules, that gas should then cool, condense, and eventually ignite into stars, creating a small, faint dwarf galaxy. The cosmic infrared background should therefore be shimmering with their combined ancient starlight, yet the glow we measure is quieter than this prediction. So where is the light from all those missing dwarfs? One startling possibility is that these small halos are not missing at all, they are simply dark. They are filled with their allotment of dark matter, but for some reason they failed to light up with stars. The process of star formation, which we often take for granted, must have been completely suppressed within them. Why would that happen? The answer may lie in the earliest moments of the universe. After the Big Bang, the cosmos was filled with a searing background radiation. In the smallest, least massive dark matter halos, the gravitational pull was simply too weak to overcome the pressure of this universal heat. Any gas that was pulled into these tiny halos would have been too hot and energetic to collapse and form stars. It would have remained a diffuse, dark wisp, forever invisible. Only the larger halos with stronger gravity could win that battle and spark with stellar life. Another, more dramatic idea involves the very first generations of stars. Their intense ultraviolet radiation could have heated the intergalactic gas to such a degree that it became impossible for gas to cool and fall into the smallest halos later on, effectively sterilizing them. This presents a profound choice for our theories. If the halos are truly dark and empty, it tells us that the minimum mass required to form a galaxy is higher than we thought, reshaping the rules of structure formation. But if the dwarfs are there and we just cannot see their faint light, it implies our understanding of how stars form in the most pristine environments is fundamentally flawed. Either way, the quiet signal in the infrared background is a direct challenge to our picture of dark matter itself. The properties of this mysterious substance determine how many small halos form and how easily they can gather gas. The missing light of the dwarfs is therefore a message, written in negative space, about the nature of the universe's dominant, invisible component. The hidden roars of these obscure giants do more than just add to the cosmic static, they actively shape the universe around them. This process is known as feedback, and it is one of the most powerful forces in galaxy evolution. When a supermassive black hole at the heart of a galaxy is actively feeding, it does not just glow, it can unleash colossal winds and jets of radiation that blast outwards at nearly the speed of light. These outflows have the power to sweep across an entire galaxy, violently pushing vast reservoirs of star-forming gas and dust out into the void. In one dramatic act, the central monster can effectively turn off the star formation in its own home, quenching the very process that built it. This is negative feedback, a self-regulating mechanism that prevents galaxies from growing too large too fast. But these same furious outflows can also have the opposite effect. As they slam into surrounding gas clouds, they can trigger shock waves that compress the material, actually sparking new rounds of intense star birth. This is positive feedback, a cosmic push that creates new stellar nurseries even as it disrupts others. The energy from these titanic struggles does not stop at the galactic border. It can pour out into the intergalactic medium, the space between galaxies, heating the primordial gas and altering its very chemistry. This galactic-scale engineering leaves a profound and lasting mark on the cosmic infrared background. The light we detect is not just the muffled glow from hidden black holes. It is also the re-radiated heat from dust that was violently stirred, heated, and displaced by these feedback processes. Every galaxy that hosts an obscured active nucleus becomes a laboratory for extreme physics, and the combined infrared echo from billions of these events is woven into the fabric of the background we observe. Decoding this specific signature is like listening for the sound of a great cosmic engine, one that both builds and destroys, whose distant hum holds the secret to why our universe looks the way it does. We have journeyed through 25 profound mysteries hidden within a faint, universal glow. From the hunt for lost galaxies and the first starlight to the whispers of dark matter and premature cosmic dust, this infrared canvas challenges everything we think we know. Each puzzle is a thread in a grander tapestry, a single question in the universe's great story. Solving one does not bring us to an end, but merely opens a door to a room filled with even deeper, more fascinating questions. Which of these mysteries do you find the most baffling? Is it the missing dwarf galaxies, the ghostly fingerprints of the first stars, or the possibility that this entire glow is the stifled roar of hidden black holes? Let us know your thoughts in the comments below. If this journey into the cosmos has sparked your curiosity, be sure to like this video, subscribe to the channel, and tap the bell so you are here for our next exploration into the secrets of the universe. The greatest discoveries are always still ahead.